Light doesn't travel. It never did. Right now you think a photon leaves the sun, crosses 150 million kilometers of space and hits your eye. You imagine it moving like a tiny bullet flying through the void. You picture it traveling at 300,000 kilometers per second, the speed limit of the universe. But here's the truth that will shatter everything you think you know about reality. That photon doesn't experience any of that journey. To the photon, the moment it's emitted from the sun and the moment it hits your retina are the same moment. No time passes, no distance is crossed. The photon doesn't travel, you just think it does. Let me show you something that will make your head spin. Einstein's special relativity tells us that as you approach the speed of light, time slows down. This isn't science fiction, this is experimentally verified thousands of times. Put an atomic clock on a fast airplane, and it runs slower than one on the ground, measurably, predictably. Now here's the kicker. What happens when you reach the speed of light? Time stops completely. From a photon's perspective, if it could have a perspective, zero time elapses between emission and absorption. The photon is created at the sun and destroyed in your eye in the same instant. No journey, no duration, no in-between. Think about that for a second. The light from a distant galaxy traveling for billions of years from our perspective experiences zero time. The photon that left that galaxy 13 billion years ago, and the moment it hits the Hubble telescope lens, same moment, no time at all. But it gets weirder, much weirder. In the 1940s, Richard Feynman developed something called the path integral formulation of quantum mechanics, and it completely destroys your intuition about how light travels. Here's what you think happens. A photon leaves point A, travels in a straight line, and arrives at point B. Simple, clean, wrong. Here's what actually happens according to Feynman's mathematics. The photon takes every possible path simultaneously. Not we don't know which path, not it randomly picks a path, it literally takes all of them at once. It goes straight, it curves left. It loops backward. It spirals. It goes to Alpha Centauri and back. It visits every point in the universe, every single path. Feynman showed this in his book QED, The Strange Theory of Light and Matter. He'd draw these crazy diagrams showing photons taking absurd routes, bouncing off mirrors that aren't there, taking detours through imaginary space. And here's the mathematical truth. You have to add up all these paths to get the correct answer for where the photon ends up. Not approximately correct, exactly correct. The photon going straight contributes to the final answer, but so does the photon that went to Mars first, and the one that looped backward in time, and the one that spiraled around your head 17 times before hitting your eye. All of them, together, simultaneously. So when you ask how does light travel from A to B, the answer is it doesn't travel. It exists at A, it exists at B, and in between is not a journey, it's a superposition of literally infinite possibilities. Let me blow your mind with Feynman's favorite example. You shine light at a mirror. The light bounces off and hits a detector. Simple reflection, right? The angle of incidence equals the angle of reflection. You learned this in high school, but Feynman asked a deceptively simple question. How does the photon know where the mirror is? Think about it. If the photon is traveling through space approaching the mirror, how does it know to follow the law of reflection? How does it calculate the angles? The answer is, it doesn't know, because it doesn't travel that way. Here's what actually happens. The photon simultaneously interacts with every point on the mirror, the top edge, the bottom edge, the middle, points that aren't even on the mirror, all at once. Each possible reflection point contributes a quantum amplitude. You add all these amplitudes together, and when you do the math, and Feynman loved showing this calculation, the contributions from most paths cancel out. They destructively interfere, except for one path. The path where angle of incidence equals angle of reflection. That path's contribution survives, not because the photon chose it, but because all the other infinite paths canceled each other out through quantum interference. The photon didn't travel to the mirror and bounce. The photon existed in a superposition of all possible reflections, and the mathematics selected which one you observe. So if light doesn't travel, what does speed of light even mean? This is where things get really strange. The speed of light, 299,792,458 meters per second, isn't the speed that light travels. It's the conversion factor between space and time. Think of it like this. Why do we measure distance in meters and time in seconds? It's arbitrary, human convention, but space-time doesn't care about our conventions. In relativity, space and time are the same thing. Space-time. The speed of light is just the exchange rate between measuring in space units versus time units. It's like asking, what's the speed of conversion between inches and centimeters? The question doesn't make sense. They're both measuring the same thing, length just in different units. Feynman would explain it this way in his Caltech lectures. Light doesn't move at light speed. Light defines what speed means in space-time geometry. And here's the really wild part. From the photon's perspective, the distance between emission and absorption is zero. Literally zero. Length contraction at light speed reduces all distances to zero. So the photon doesn't cross 150 million kilometers. From its perspective, the sun and your eye are at the same location. No distance, no time, no journey. Now I'm going to tell you something that sounds like insanity but is actually serious physics. In 1945, Feynman and his mentor John Wheeler proposed something called the Absorber Theory, and it suggests that light doesn't even go from past to future. Here's the idea. When you emit a photon, it sends waves forward in time toward the absorber, but it also sends waves backward in time from the absorber to the emitter, both directions, simultaneously. These forward and backward waves interfere with each other. They create what looks like a photon traveling from emitter to absorber, but it's not actually traveling. It's a standing wave pattern in space-time connecting two events. Think of it like this. You pluck a guitar string. Did the vibration travel along the string? Or is the whole string vibrating as one system? The photon is the vibration, space-time is the string. Feynman eventually moved away from this interpretation, but the mathematics remains valid, and it reveals something profound. The emission and absorption of light might not be two separate events connected by travel. They might be one single event in space-time that we perceive as separated because we're stuck experiencing time sequentially. The photon leaving the sun and hitting your eye aren't connected by a journey. They're the same quantum event stretched across what we call space and time. So what does this mean for everything you see? Right now, you're looking at your screen. You think you're seeing it because light traveled from the screen to your eyes. But according to everything I just told you, that's not what's happening. Instead, there's a quantum correlation between the electrons in your screen and the molecules in your retina. This correlation exists as a superposition of infinite possible paths. The mathematics of quantum field theory determines which correlations are observable. You interpret this as light traveling. But it's more accurate to say reality is a network of quantum correlations, and your brain interprets certain correlations as seeing light move. Feynman would put it more bluntly in the character of physical law. Things on a very small scale behave like nothing you have any direct experience about. They do not behave like waves, they do not behave like particles, they do not behave like clouds or billiard balls or weights on springs, or like anything that you have ever seen. Light isn't a thing that travels, it's a pattern of correlations in quantum fields. And here's what really breaks your brain. This means causation might be an illusion too. You think the sun emits light, then that light travels, then it hits your eye. Cause, journey, effect, past, present, future. But if the photon experiences zero time, and if Wheeler-Feynman is even partially correct, then emission and absorption are correlated events with no clear causal order. The absorption might cause the emission just as much as the emission causes the absorption. Time's arrow might just be the direction your consciousness happens to experience correlation. Remember at the start when I said light doesn't travel? Now you understand what I meant. Tomorrow, when sunlight hits your face, you'll think light traveled 8 minutes from the sun to reach me. And in a practical sense, for human purposes, that's fine, that's useful, that's how we navigate reality. But now you know the deeper truth. That photon experienced zero time. It took every possible path. It doesn't move through space. It correlates 2 points in space-time. The emission and absorption might be the same event viewed from different angles in space-time geometry. The sun and your face aren't connected by traveling light. They're connected by quantum field correlations that we interpret as light travel because our brains evolved to model reality that way. You are not seeing the sun as it was 8 minutes ago. You are experiencing a quantum correlation between nuclear fusion events in the sun's core and chemical reactions in your retina. The 8 minutes is how we measure that correlation using human time units. But to the photon, it's instant. As Feynman wrote in QED, I think I can safely say that nobody understands quantum mechanics. He spent his life calculating how light behaves with incredible precision, but even he admitted the why remains mysterious. Light doesn't travel like a bullet. It doesn't wave like water. It doesn't flow like a river. It correlates. It superposes. It interferes. It connects points in spacetime through quantum amplitudes that, when you add them all up, create what we call seeing. You are made of atoms that are mostly empty space. The light hitting you passes through that emptiness, or maybe it doesn't pass through at all. Maybe it just creates a correlation between the electromagnetic field out there and the electromagnetic field in here. And the boundary between out there and in here? That might be an illusion too. Feynman loved to end his lectures by saying, "Nature's imagination is far greater than man's." He spent decades studying light, won the Nobel Prize for it, and still marveled at how strange it actually is. Light doesn't travel. It reveals that space and time themselves might not be what we think. You are not a separate observer watching light move through empty space. You are a pattern of correlations in the same quantum field that creates what you call light. The photon doesn't journey, neither do you. You're both waves in the same ocean, briefly creating the illusion of separation, and that's far more beautiful than light just traveling.